Today I will be talking about 8 topics: electromagnetic induction, AC generators, and transformers. Electromagnetic induction is simply the ability of a magnet to create a current inside a conductor. Scientists like Ørsted have already shown that if you have a current in a wire, it will create a magnetic field. So a current can have magnetic fields. But scientists like Faraday wondered, could you produce a current from a magnetic field?
In other words, is the opposite true?
In 1831, Faraday did an experiment with coils of wire wrapped around an iron ring. So connecting this to a battery will produce magnetic fields over the left side. So he was hoping that the current will be induced on the right side. But no such current was observed. However, Faraday did notice that a small current was induced only during the opening and closing of the switch of the current. Also, he noticed as the magnet is allowed to enter the coil, a current is induced and is registered by the galvanometer. If the magnet is then pulled out of the coil, the current is induced in the opposite direction. But if the magnet is then placed near the coil and does not move relative to it, nothing happens, no current is induced. Also, if we move the coil towards the magnet, we again find a reading. This indicates that it is the relative motion of the coil and the magnet that is responsible for the electromagnetic induction. To understand the electromagnetic induction, we need to understand the concept of magnetic flux. Magnetic flux is defined as the magnetic field strength times the area swept out by a conductor. In other words, it's the magnetic field lines that cross or pierce the loop area. Mathematically, magnetic flux is defined as the product of the strength of magnetic field B and the surface area of A multiplied by cosine theta, where theta is the angle between the magnetic field direction and the direction perpendicular to the loop area. Phi equals BA cosine theta. The unit of magnetic flux is the Weber WB or Tesla meter squared. This means that the maximum flux through the loop occurs when theta equals 0 degrees, which is when the magnetic field is perpendicular to the loop area and its value is BA. And it is 0 if the magnetic field is along the plane of the loop where theta equals 90 degrees. So what is the connection between magnetic flux and electromagnetic induction? Moving the magnet or the wire will change the magnetic field, which will then change the flux and hence induce the current. Thus, the induced EMF equals the rate of change of the magnetic flux through the loop. This is what is known as Faraday's law of electromagnetic induction. If EMF is induced in a conductor, there will be current as well. One very important application of electromagnetic induction is the AC generator or alternating current generator, the method that is used universally to produce electricity. A coil is made to rotate in a region of magnetic field. This can be accomplished in a variety of ways, such as a diesel engine burning oil, by falling water in a hydroelectric power station, or by wind power, etc. The ends of the coil are firmly attached to two slip rings that rotate along with the coil. The slip rings touch carbon brushes that transfer the current to an external circuit.
The function of the slip rings is to maintain constant contact with the same side of the coil.
According to Faraday's law, as the coil rotates, the flux in the coil changes, so the EMF is produced in it. As one side of the coil moves up through the magnetic field, a potential difference is induced in one direction. As the rotation continues and that side of the coil moves down, the induced potential difference reverses direction. This means that the direction of the produced current is constantly changing. This is alternating current or AC. The induced voltage N is as a result of the magnetic flux change through the loops of the coil during time interval dt. Applying Faraday's law,
the voltage is going to be the first derivative of magnetic flux, where magnetic flux equals NVA cosine theta. Make use of angular speed, so theta equals omega times t. We get the induced voltage will equal NBA omega sine omega t.
The maximum voltage produced by the generator equals NBA omega.
The maximum potential difference or current can be increased by increasing the rate of rotation, increasing the strength of the magnetic field, or increasing the number of turns on the coil.
These two graphs show that the induced EMF is 0 whenever the flux is maximum or minimum, and conversely, it is maximum or minimum whenever the flux is 0. Also, it's worth to note that the voltage can be negative as well as positive. This is what is called alternating voltage, and the current that flows through the coil will be going to be alternating current AC as well. The peak current can be calculated from maximum voltage divided by resistance as current equals. So what are transformers? A transformer is a device that takes a certain AC voltage as input and delivers a different AC voltage as output. Basically, it consists of two coils wrapped around a common iron core. The primary coil is the one connected to the input of the source. So how does it work? The input generates an alternating magnetic field in the iron core. By Faraday's law, then there will be an induced EMF in the output coil. So the transformer only works when the voltage in the primary coil is changing. Then the transformer will not work with DC or constant voltage in the primary coil. Then the output or the secondary voltage can be in this ratio or formula, where the voltage is directly proportional to the number of turns, and inversely to current assuming no power loss.